Log on, tune in, find out. Another good idea from Cambridge.
Grant Reinman, from Pratt and Whitney, and if you had problems getting over here because of plane engine problems, Grant said, talk to him and he'll take care of it. And he'll be speaking on design for variation.
Actually, they were probably GE engines.
I told you he'd take care of it.
Better than the plane.
We'll get started. We actually work at Pratt and Whitney.
Put the microphone on.
Oh. Okay. See, you end up all of a sudden. I just stick that in my pocket. Is it on?
Okay, can you hear me? All right. Okay, I work at Pratt Whitney. We used to be Pratt Whitney Aircraft, and now we're just plain old Pratt Whitney. And Pratt Whitney is the world's largest laboratory or incubator for model calibration and emulation methods. And we also produce jet engines and rocket engines at the same time. But I like to think of it as my own personal laboratory for all the methods that have been developed over the last several years. But in the meantime, we do make something of value every now and then. We make jet engines, these liquid rocket engines on the back end of the space shuttle are ours, as are a whole lot of commercial and military jet engines. Okay, in engineering, so the entire title of this seminar was Accelerating Industrial Productivity via Deterministic Computer Experiments and Stochastic Simulation Experiments. Well, I'll tell you just a little bit about how it has accelerated our industrial productivity. This was sort of a last-minute presentation, so that means a couple of things. That means that some of these slides are as new to you as they are to me, nearly. And number two, that I wasn't able to add a lot of fresh content to it, unfortunately, because it takes a month to get through our legal staff and our legions of vice presidents and so forth. But be that as it may, in engineering, prior to the use of probabilistic methods, the engineers have long recognized that they have issues to contend with due to variability in the real world and uncertainty in their models. And they've traditionally approached those using design margins or factors of safety. And here just a sampling of the types of things that we've had to contend with. Manufacturing, variation due to variation in manufacturing processes, variation in the way our customers use our product, and variation in material properties is just a very small sampling of what we have to contend with every day. But those traditional methods only get us so far. Number one, if you add design margins or factors of safety, how do you know how much is enough? For a given new engine design, should I double, triple, or halve my traditional design margins? And so in order to avoid those sorts of questions, we really need to do things probabilistically. And the first person, to his credit, to really discover this from the engineering perspective in our organization was our senior vice president for engineering, who about 2 or 3 months after getting into his job, shut himself in his office for a weekend, went over all the issues that had come across his desk in those first 2 or 3 months on the job, and asked himself, what was in common? What are the common threads running through all these engineering issues that I've had to contend with? And his answer to that question was every single issue only had one thing in common, one or two things in common. It was either variability that hadn't been designed adequately against or tested adequately against, or uncertainty in models that wasn't adequately accounted for. Okay, so he was my first benefactor who got us started, and that was a few years ago when we actually got a little bit of development money, and we started something called the Uncertainty Quantification Initiative, where we just had to decide how we were going to quantify uncertainty. What paradigm do we use? Do we use fuzzy math? Do we use the Bayesian paradigm? Do we use a frequentist paradigm? That sort of thing. So we spent about a year answering that question. And then my second benefactor came along, our next vice president of engineering, who took me under his wing and said, you know something? This can pay for itself. It doesn't have to cost engineering a cent. And he said the reason it can pay for itself is when you do one of these variance-based sensitivity analyses, you always show me this nice Pareto chart. We're always worried about things on the exciting end of the Pareto chart, things that make a real difference. But he said, don't neglect things that are on the far right-hand side of that Pareto chart. That's where you're going to pay for yourself, Grant. He said, that's where these are things that we might spend a lot of money controlling in production or in engineering that are really having very little impact on the product. And in fact, we found one tolerance that we were holding to tenths of thousandths of an inch on one bearing in one commercial engine, where if we were able to relax that tolerance just a small amount, and it was about a $300,000 a year savings in that one tiny little tolerance. So that paid for much more than myself. Okay, and lastly, there are certain problems that can only be approached probabilistically. Jet engines, as you'll see, have one thing in common. You'll see rotors, rotating airfoils, and stations of stators where we might have nominally 70 identical stators in one position in the jet engine. These are 70 nominally identical parts, but they vary slightly because of production differences or manufacturing quality differences. However, in the real world, that rotor life is going to depend on, in other words, how long that engine stays in service is going to depend on the airfoil with the maximum amount of distress or the minimum life. That means that we are going to have a weakest link structure throughout that gas turbine engine. And if you don't approach that problem probabilistically, then you're not going to solve this problem. So we found that simply understanding that variation from one airfoil to another and reducing it without doing anything to the level of engineering technology in the engine, we can easily double the life of the rotor by just understanding that variation from one airfoil to the next. Okay, so once all of that pre-work took place several years ago, we were given the uncertainty quantification project, which then, once we graduated from that and demonstrated that we had the ability to understand and model variation and uncertainty, this has turned into the Design for Variation Strategic Initiative at Pratt. Now we've graduated. We're no longer a demonstration project. We're actually changing the way that engineers design parts for gas turbine engines. So our strategy was first to identify all the key modeling processes throughout Pratt and Whitney. Second was to tell them what they needed to do to their processes. Do we need to invest in all new finite element software, or do we need some sort of probabilistic computational fluid dynamics? So we had to answer those sorts of questions. And then finally, provide resources under this strategic initiative for these key processes to modify themselves. So this slide just shows that cut away from a typical gas turbine engine. And you can see the problem I was talking about. You might have 50 airfoils here, 40 here, and it varies by stage. But the weakest link structure is pervasive throughout the engine. And this shows that it also shows that we're working on probabilistic design in every single aspect of gas turbine engineering. There's not one that hasn't been affected now. And at the nose cone out here, we have our DFV, or Design for Variation Infrastructure team, which is comprised of a small group of statisticians, as well as our partners in high-performance computing, training, and other areas of the company. And I'll go into that in a little bit more detail. Okay, I had indicated there that we had to change the processes somehow. This was a very large undertaking. You're talking about deterministic engineering design processes that had been embedded in the company for dozens of years. And to change those was not going to happen overnight, first of all. It happened over a period of years, and we had to give them, in essence, here's what we need to do in order to move from a deterministic design-based process to one that's probabilistic. So we gave them criteria that they had to meet in order to become a DFV-enabled modeling process. And so here's their checklist. Notice that we would not let them design parts without having a calibrated physics-based model. So they couldn't just enable their models to do things probabilistically and run off with them. They had to be calibrated. And that means that we had to have test data or some type of real-world data that was brought together with their simulations in order to calibrate, bias correct, and quantify all the important sources of uncertainty in their model. Okay, and design for variation, the process that we developed has these 5 components to them. We don't just analyze using the process that I'd laid out on the previous page. We actually have to start with defining the customer's requirements. Now, we're moving into a deterministic engineering world where even a lot of our requirements are deterministic. So, for example, we go back to the customer, and on a particular airplane, they had a rigid requirement that no more than 500 BTUs worth of heat could be returned to the fuel tank. So we use jet fuel, not only for the obvious reasons, but to produce thrust, but we also use it to cool some jet engine components. So as that fuel cools the components, it picks up heat and returns that heat to the fuel tank. So we had a deterministic requirement that the Air Force had given us, that you can't exceed so many BTUs returned to the tank, period. But everybody knows that probabilistically speaking, on rare occasions, we exceed that. So the first thing that we have, the first task here, was to define how much or what frequency is an allowable frequency. That got into some interesting decision theory problems. So we formulated it as a decision theory problem. We involved our customers, our engineers, and solved it. So that we need that to have a design allowable to start with. And then, of course, we go through the analysis process, and we solve. So we find the optimum design. Though that in and of itself is a very difficult problem. This is the robust design, or what exactly does it mean to optimize a system probabilistically? There are any number of ways of formulating that optimization problem. And then, of course, we have to verify and validate and sustain our model over long periods of time. Since these aren't research projects, we're using them to design jet engine parts. We also have to monitor the processes, the real-world processes that were important, that our variance-based sensitivity analysis told us were important to the lives of these components. We have to make sure that we monitor and sustain and control those that are under our control. And if they're not under our control, we certainly have to monitor them. Okay, and this is just a summary of our analysis step, where all of this should look somewhat familiar to a lot of folks here, where we do things like design space-filling experiments over a large model input space. We execute that experiment, running that experiment through the engineering model, and this is where we use our friends in high-performance computing's help to distribute these jobs over things like clusters of computers. And then we develop a model emulator and perform a sensitivity analysis. The sensitivity analysis then directs us to what inputs are critical to this particular design. We focus and refine our input probability distributions for those inputs. We also perform the Bayesian model calibration. And by the way, as a result of our uncertainty quantification effort, we've decided our entire uncertainty quantification paradigm is Bayesian. So the entire thing from beginning to end is one very large Bayesian paradigm. And then, of course, in the end, we do our real-world uncertainty analysis, and we differentiate between probability statements that we make in the virtual world and probability statements that might be able to hold some water in the real world. So back here, we might do some virtual uncertainty analysis, but it's only after we do the Bayesian model calibration that we can make statements that might make sense in the real world. Okay, I told you we have an infrastructure organization, and this has been extremely important. Without this, we couldn't have executed at Pratt. And we do things like develop and maintain software. And this is a little bit of our software suite that we use. So we have a lot of tools that are built in R and MATLAB, for example. WinBugs is used frequently. Of course, GemSA and GPMSA. GemSA, which came out of Sheffield, and GPMSA from Los Alamos are frequently used pieces of our toolkit. Also, we use the EyeSight FD software. That links multiple codes together. In every one of these disciplines, one thing that we found that was interesting was that we don't, in any design task, there's never just one code that's being calibrated or used in the design process. There's always multiple codes. And on average, you might have anywhere between 6 and 10 codes that are put together in order to design for a given criteria. And then, of course, there's SAS, and we're still trying to get SAS interested in solving certain computational problems for us. We need a little bit of help there. If anybody in the audience is from SAS, I'd like to talk to you. Okay, and then we're developing our own in-house codes now called Beckham. And we'd like to actually enclose that in a little football, but we might run into a few problems there. It stands for Bayesian emulation and calibration of computer models. So what we're trying to do is create a system that will do full Bayes or modular Bayes, and will do steady state and transient analysis, just basically an entire toolkit for emulation and calibration of computer models. And let's see. So we've also set up a series of introductory and detailed training classes. That this guy is just a pure introduction to uncertainty analysis and sensitivity analysis. But then we get into practitioners classes, and these are multiple day classes where we get engineers in there and we teach them how to do basically 90% of the job, which is things that are crucial to the performance of sensitivity and uncertainty analysis that we can put in their hands, because with 3,500 engineers on site, there's no way we can assign a statistician to everybody who's working this. So we found that we have to develop a fairly high level of training amongst our engineers, and in order to make this work. And then, of course, we can't leave the managers behind. If we do that, we're bound to fail. So we've developed an introductory class for managers and a guide to asking the right review questions. So we have to let the managers know, what are the right questions to ask? Where could a probabilistic analysis fail? And believe me, these guys are hard. Okay, and of course we provide project management as well as technical assistance. We help write work procedures. We run a wiki page that lets people know what's going on, how to run software, that sort of thing. And then we always have to worry about input data. The input data required for these analyses is fairly large. So that's a fairly large job in and of itself. Okay, this is just an example of, in our training classes, we try to find small problems that have high pedagogic value. And that is those problems that are easy to wrap your head around the physics, but yet contain a lot of good lessons in terms of the overall sensitivity and uncertainty analysis process. One of those that was very interesting was published by a couple of physicists in an applied physics journal a few years ago, where they had come up with a new way of solving the beam deflection problem when you load a beam both uniformly and with a concentrated load. And that's a solved problem. Bernoulli solved it 300 years ago. But these fellows came up with a new way of looking at it. Instead of using bending moments, they used the shear force formulation. It got you away from some nasty elliptic integrals in the solution. But the nice thing about it for us was that it was a very nice, neat problem setup. They had one variable input, the concentrated load. They had one calibration input, which was Young's modulus for this particular beam. And best of all, They gave us an idea of how to set up the physics, so we had to set up the code ourselves. But they gave us some real-world data. They had run an experiment also to validate their model. So this is so we've sent a thank you note to them, and we told them that it helps engineers to be able to see things on a small scale, what they'll have to contend with on a large scale. Things like, how do you choose that prior distribution for Young's modulus in this case? How do you go about that and do a serious job of it? It helps to understand the nuances, things like the high prior theta delta correlation, the posterior correlation between the model parameters and this discrepancy function, and to understand and we have lively conversations about this, what to do if we find a significant discrepancy function. What do you do with that in an engineering environment? Do I incorporate that discrepancy function into my design, not knowing the physics behind that discrepancy function? Are they comfortable using it? So we get into some pretty lively discussions, especially since in this cantilever beam problem, there actually is a small but significant bias or discrepancy function running around. Okay, applications. We've had hundreds, if not, we might be getting close to thousands of the 1,000 number of applications now. We've used it at Pratt for reliability improvement and problem avoidance. We know we've already avoided at least a couple of fairly catastrophic problems by running through this analysis. We've used it for robust design. We've used it in many places for cost reduction. And this is interesting. I found that give a tool time and it will grow. Its sphere of influence will just get larger and larger. So how is it growing? It's growing. This effort's growing in two different ways. Number one, it's going cross-disciplinary. Once engineers have learned what emulators are and how to use them, they'll want, okay, so I have a structural emulator here. Maybe I can emulate my aerodynamic characteristics of the part, and I can put them both together and optimize both for aerodynamic properties as well as for structural properties as well. And then I can enlarge it another way and go to subsystems. So I've got emulators for turbine life, and I can couple those with combustor and compressor emulators, put the whole thing together and do subsystem optimization. So that's been pretty exciting. We're using them, in manufacturing, in process control. We're using them to decide what to measure and what not to measure. In engineering models, instead of just emulating the things that are important to engineers, design criteria, they're also adding models or submodels for the quality criteria, the things that are measured on the shop floor. And so we're learning a lot of interesting things like how well correlated are the things that we measure on the shop floor to the things we care about in the real world. So is measuring this particular thing on the shop floor really of value? Does it really correlate well with life? So for turbine airfoils, we are completely redesigning what we do on the shop floor as a result of this. We're also doing proactive manufacturing. We've got a series of emulators within a Bayesian network that tell for a part flowing through a manufacturing process, we can predict how it's going to come out of that process in the end so that we can send it through a different set of gates if it needs to, and it'll come out a higher quality airfoil in the end. Let's see, and then in service, these are some of my favorites. We've got onboard health monitoring and life prediction due to these emulators. So we're actually onboard calculating structural lives using these emulators and all the data that are flowing into it. And then an effort that we just finished up was we designed our first self-calibrating models, where as the models are residing on board real time in the engine and they're collecting data, they're self-calibrating to that particular engine serial number. So it enables you to predict the performance and life of various turbine engine components. And I thought as one last example, I would show you we've developed a very complete system for the prediction of high cycle fatigue risk. In the jet engine world, this has remained one of the last unsolved problems. which is predicting high cycle fatigue, which is nothing more than think of a part vibrating at very high frequency and developing cracks as a result. And sometimes this happens very unexpectedly. Well, we've spent a couple years putting together a complete high cycle fatigue model with a computational fluid dynamics-based forcing model, a mistuning model. Sometimes you can have these airfoils in a rotor where just the way that you arrange the airfoils in the rotor will affect the vibratory response of the entire rotor. It's a concept called mistuning. And so we'll have, and we have damping models, measurement models, steady stress and vibratory stress models, models for how the customer uses the particular engine, and then material characterization. That's getting really interesting. Materials have been characterized empirically for decades now. We're now moving into physics-based material models where we're able to predict the physical characteristics of materials using physics-based models. And that's an area of recent focus. And then finally, in the end, I'm going to talk more about these tomorrow, I believe. We have a long list of challenges that we'd like to put out to the community that ranges, it crosses the board. One of the more interesting ones is we're learning how to measure parts very efficiently. Now we can capture the external shape of a complex turbine airfoil almost instantly as they come off the manufacturing line with using things like white light inspections that will capture or will nest this part at 40 to 100,000, sometimes 200,000 inspection points, and it will automatically create a finite element mesh for that part, and it will solve thermal and mechanical stress problems right there. And we're doing that with emulators as well. But this also presents us with some nice problems. Well, one of our inputs to our model is now an array of size 40,000 or 50,000 or 70,000. We need we need compact but informative representations of those probability distributions of the external and internal shapes of the components. And we already have at least one mathematician on board working on different ways of representing that variability in three-dimensional space, internally and externally. But I'll talk about that some more tomorrow. Okay, this is one of my favorite quotes from Peter Bernstein. Okay, any questions?
We have time for one question, and if you have others, we can defer that until the coffee hour. Yes.
Okay.
Did I see a hand up?
Yeah. You mentioned using decision theory and
Yes.
listing up some utilities from clients. Have you looked at, rather than variance-based sensitivity, considering how inputs contribute to decision uncertainty? Or are you just using only variance-based measures of importance?
Right, we have not. So this is an area that we really that hasn't received a lot of attention. So any ideas that you'd like to recommend, feel free to catch me later on. And that's an area that I would really love to talk to people about, because we have dozens of criteria that are purely deterministic right now, that are not well posed. Okay, thank you.